So we're looking at Euler paths, Euler trails. We had talked about the problem of Leonhard Euler. He was going through the city of Königsberg and he wanted to figure out, could he cross every bridge exactly one time without double crossing? We're going to try to answer that question later. So remember what an Euler path is. An Euler path is a path that visits each edge of your graph exactly once. And an Euler circuit is an Euler path that begins and starts. It begins and ends in the same place. So it visits every edge exactly once, and it begins and ends in the same place. That's what an Euler circuit is. So here's a criterion for having an Euler path. Let's do an Euler circuit first. I'll call this the Euler Circuit criterion. Euler Circuit criterion. So when do you have an Euler circuit? That means when are you able to visit every edge exactly one time without double crossing edges and start and end in the same place? Now this is when first of all you have to have a connected graph, so you can't have any disconnections. A connected undirected graph with n greater than or equal to 2 vertices, so at least 2 vertices, has an Euler circuit. Precisely when, that's if and only if and only if, each vertex of the graph has even degree. So if every vertex has even degree, then you're going to have an Euler circuit. Okay, here's another theorem. This one is about when do you have an Euler path that doesn't begin and end in the same place. So an Euler path that's not an Euler circuit. Euler path having different beginning and ending, having different beginning and ending. What's the criteria for that exactly? Well, it's the following. First of all, you have to be a connected graph. You can't have any disjoint pieces of your graph. So a connected, undirected graph has an Euler path that is not an Euler circuit, has an Euler path that does not begin and end in the same place. That is not an Euler circuit. If and only if there are exactly 2 vertices of odd degree. There are 2 vertices of odd degree. All the rest would be of even degree. There are 2 vertices of odd degree. Okay, so there are your 2 big criteria. One is for the Euler circuit. That's a Euler path that begins and ends at the same place. So you have to check to see if every vertex has even degree. And for an Euler path that doesn't begin and end in the same place, you want to check that you have exactly 2 vertices of odd degree. So let's see, are there some things can we find some Euler paths and some Euler circuits maybe? Let's do some exercises. We want to consider the graph. Determine if the graph has an Euler path or an Euler circuit. If the graph has an Euler circuit, just an Euler path without the circuit, or neither. If it does have a Euler path or an Euler circuit, construct the path. The circuit or path. All right, here's number 1. So I got A, B, C, D. And then underneath that, I got E, F, G, H. A goes to B, B goes to C, C goes to D, D goes to H. G goes to H, F goes to G, E goes to F, A goes to E. E goes to B, G goes to D, C goes to G. The vertex right there. B goes to F. A goes to B, and E goes to F. Oh, there's one more. C goes to D. So does this have an Euler path? Does it have an Euler circuit? Or does it have neither? So first of all, we want to note it's connected, right? It's connected. The graph is connected. That's the first thing. Graph is connected. If there's a disconnection, you're not going to have any Euler path or Euler circuit because you won't be able to travel from one side of the graph to the other side of the graph, the disconnected pieces. All right, now we're going to look at the degree of all the vertices. So I'm going to look at the degree of the vertices. We'll get the degree of A, degree of B, degree of C, degree of D, degree of E, F, G, and H. Let's count the degree of A. So A has degree, 1, 2, 3. Has 3 edges coming out of it. B has degree 1, 2, 3, 4, 5. C has degree 1, 2, 3, 4 edges. D has degree 1, 2, 3, 4 edges. E has degree 1, 2, 3, 4 edges. F has degree 1, 2, 3, 4 edges. G has degree 1, 2, 3, 4 edges, and H has degree 1, 2 edges. So notice they're all even except these first two, right? A and B have an odd degree. So since the graph has 2 odd degree vertices, what can we conclude here? And the graph is connected, of course. Since the graph has 2 odd degree vertices and it's connected, then what can we conclude? Right here. If there are 2 odd degree vertices, there's an Euler path. That's not an Euler circuit, right? Then there is an Euler path. An Euler path. That is not an Euler circuit. That is not an Euler circuit. Okay, so once we have verified by that theorem that there's an Euler path, we want to construct an Euler path. So what you're going to do, you're going to start on one of your odd degree vertices. So we're going to start on A, let's say, and end on your B. You're going to start at A and you're going to end on B. And you're going to have to trace the entire graph. So we're going to start here. You can start at B or end on A. Doesn't matter. So I'm going to start here at A. And I can go anywhere I just got to make sure I don't box myself in. You have to be careful not to box yourself in so you can't move anymore. You got to make sure you can constantly move. So we want to go from A and end at B, right? You want to start on your one odd degree vertex and then end on your other odd degree vertex. So I like to go around the outside. I'm like an old man, and you know, old people, they don't like to get into the middle of the city, right? They like to drive on the outside of the city where it's kind of slow and easy. That's me. So I'm going to go from A to E. Comma, I'm going to go around here, E to F. F to G. G to H. H to D. D to C. C to D. D to G. G to C. I have to visit every single edge. Every single edge. Where am I? See, I'm going to go from C to, only have one way I can go, C to B. From B, I have several options. I can go, let's say, up around to A. From A, I only have one direction I can go. I can go back to B. And from B, I have two options. I can go down to F, or I can go down into the left to E. I'm going to go down into the left to E. From E, I only have one option, forward to the right, F. And then from F, I only have one direction, back to B. So there is, right there, that is my Euler path. That's not an Euler circuit, right? We ended in a different spot than we started. So you're going to end on one odd degree vertex. You're going to begin on one odd degree vertex. That's what's going to happen when you have an Euler path. It's not an Euler circuit. Now, if you have an Euler circuit, you're going to start and end on the same vertex. All right, let's do another example. Number 2. Okay, I got a strange looking graph here. We got A, B, C, D, E, F. We go A to B, B to C, B to C. We have a multi-edge there. We're going to go B to F. We're going to have a multi-edge there. A to F, F to E, D to E, C to D, C to E, B to E. Am I missing any? F to D? I got a C to F. No, that didn't turn out too well. Let me try to straighten that up a little bit. All right. Oh, right. And there's one more, A to D. I think this is my graph here. So first of all, this is connected, right? So this graph is connected. The graph is connected. So you have to make sure your graph is connected before you can even consider the possibility of there being an Euler path or an Euler trail. So the graph is connected. There are no disjoint pieces of the graph. The graph is connected. All right, so then we're going to look at the degree of every vertex. Look at degree of A, degree of B, degree of C, degree of D, degree of E, degree of F. So A has degree, let's count. 1, 2, I think I'm missing an edge here. Oh, I forgot to do A to C, my bad. Let's do A to C here. Okay, let's count the degree of A again. It's going to be 1, 2, 3, 4. B is going to have degree 1, 2, 3, 4, 5, 6. C is going to have degree 1, 2, 3, 4, 5, 6. D is going to have degree 1, 2, 3, 4. E is going to have degree 1, 2, 3, 4. F is going to have degree 1, 2, 3, 4, 5, 6. So So notice how all the degrees are even, right? These are all even. That should be exciting. When you have all even degree vertices, you can conclude when you have a connected graph with all even degree vertices, since the degree of every vertex is even, the degree of each vertex is even, then the graph has an Euler circuit. Remember that? Where was that? Where was that? Aha. If each vertex has even degree, then there's an Euler circuit. All right, so we know there's an Euler circuit in here. So we gotta do an Euler circuit. We gotta construct an Euler circuit. So an Euler circuit is a Euler path that starts and begins in the same place. So we have to visit every edge exactly one time. We have to start and begin in the same place. Where do you want to start? You can start anywhere. Anywhere. When you have all even degrees, you can start anywhere. So I'm going to start here at the bottom of F. What the hey, man? What's up? F? I'm going to stay around the outside because I'm an old dude. I like to drive on the outside here where not too much traffic. I'm going to go from F to E, E to D, D to C, C to B, B to A. I'm going to go A to F. I'm going to go up here to B, F to B. I'm going to go from F to C. I'm going to go from C to E. I'm going to go from E. I only got one direction I can go with E. I have to go from E to B now. I'm at B. I just have, it looks like one direction I can go. I can go back to F, B to F. From F, I have a couple of directions. I can go north to C or northeast to D. I'm going to go northeast to D. Then from D, I only have one direction I can go. I can go from D to A. And from A, I only have one direction I can go. I can go from A to C. And from C, I only have one direction. I can go south to F. And that's where I started, right? I started at F, I ended at F, and I've traced the entire graph exactly, each edge exactly one time. There's my Euler circuit. Circuit begins and ends in the same place. All right. All right, let's do one more graph. So here we're going to have A, B, C, D. It's not writing. E, F, G, H, I. So it's definitely connected, but let's start looking at the degrees of the vertices. Degree of A is what? 2. Degree of B is 3, right? So A was 2. B was 1, 2, 3. C is 1, 2. D, what about D? 1, 2. Degree of E. 1, 2. Degree of F. 1, 2, 3. 3 edges coming out of F. Degree of G. 1, 2. Degree of H. H has what? 1, 2, 3, 4. And what's the degree of I? I has what? 1, 2, 3 edges coming out of it. So you want to focus on your odd degree vertices when you're looking for Euler paths or Euler trails. We got one here, another here, another here. Looks like I've counted wrong. Let's see, my degree of A was 2, my degree of B was 3, Degree of C was 2. Degree of D was 3. That should have been a 3 right there. Degree of D should have been 3, right? If you count, let's do that one more time. 1, 2, 3. Yeah, it should have been 3. Now, how did I know something was wrong? I knew something was wrong because you only have an odd number of odd degree. You never have an odd number of odd degree vertices. You always have an even number of odd degree vertices. Odd degree vertices come in pairs. They come in pairs. So, I knew something was wrong because I had an odd number of odd degree vertices, so that was incorrect. So now that I have an even number of odd degree vertices, I know I'm okay. So the question is, do I have an Euler path? Do I have an Euler circuit? No. Right, we have more than two odd degree vertices, since there are more than 2 odd degree vertices, then there is no Euler path. Or Euler circuit for that matter, or Euler circuit, right? Euler circuit is a special type of Euler path. So an Euler path that's not an Euler circuit just has 2 odd degree vertices. An Euler circuit has 0 odd degree vertices. So if you have more than 2 odd degree vertices, you will not have an Euler path or an Euler circuit at all. All right, so asking the question. Back to, what's his name's problem? Euler's problem. So here you had what? The river. Here you had the island. Here you had the other island, right? And you had the bridges. So is it possible to go across each bridge exactly one time? Let's call this northern land A, this island here B, this southern land C, and this island here on the east side D. So you can write A, B, C, and D. And you can connect those with these edges. So you got what? A to B, A to B, B to C, B to C, B to D, A to D, and C to D. So this is the graph that represents the Königsberg problem. So this is sometimes called the Königsberg multigraph. The Königsberg multigraph. It's a famous graph. Königsberg multigraph. So how can we show that there's not a way to walk across those bridges exactly once? You just look at the degrees of the vertices, right? Degree of A is 3. Degree of B is what? 1, let's count. 1, 2, 3, 4, 5. Degree of C is what? 1, 2, 3. Degree of D is what? 3. So you got too many odd degree vertices, right? We have too many odd degree vertices since there are more than 2 odd degree vertices. There is no Euler path. So that means there's no way to cross every single bridge exactly one time without double crossing. Yeah, so there's the answer to Euler's famous bridge problem right there.